All right, here we go, my AP Chem folks. Today is Monday the 14th. It's an A day. I'm having fun with you guys. I'm enjoying everything we're doing virtually and face-to-face. I feel like I've got some strong students. I feel like you guys are in it to win it. And I think you guys will take the opportunities to do well. I feel like we're going a little slow, but that's okay. I feel like we need to reinforce the concepts. So today we're going to review Chapter 3 concepts that we did last week. We're going to kind of touch on them, and I want to reinforce the steps and the problems. Okay, and then we're going to look at some new stuff. So we'll do percent composition, empirical formulas, balancing equations, combustion analysis. We might even get into some stoichiometry. So I need students to watch this video during class today. Okay. So students will be able to determine average atomic mass, interpret mass spec graphs. We spent a lot of time on that on Friday. Students will be able to convert between moles and mass and atoms, calculate molecular mass or molar mass, determine the percent composition, balance chemical equations, determine the empirical and molecular formulas of a compound, and then we'll talk about combustion analysis and stoichiometry. We'll see what we can get to. Okay, so average atomic mass was the weighted average based on isotopic composition. So different isotopes have different weights. And so if you have an isotope that is very common, let's say it's 90%, and that isotope is heavy, what that means is that isotope will bring the average up. So it's a weighted average. So isotopes that have more abundance and more mass will bring the average up. Isotopes that are lower will bring the average down. So it's not a normal average like grades, right? If you have grades, tests, let's say you had 4 tests for a semester, your average would be equal weights, right? Each test is equal weighted. So you take the sum of those 4 scores and you divide it by 4 and you get the average between them. That is a regular average. This is a weighted average, so this is different, okay? The way that we calculate this is percent isotope A times the mass of A. Remember that percent has to be as a decimal. So if it's 90%, what I'm going to put in this equation is 0.9. I'm not going to put 90. Okay? So make sure it's represented as a percent out of 100. The number itself that you put in the equation. Times the mass of A plus isotope B times the mass of B, and so on. You continue to add the percent of the isotope times its mass for every isotope that you have. And then that will equal your average atomic mass for that element. And this is why they're not whole numbers. You remember me asking you guys why they're not whole numbers? This is why, because it's a weighted average, and you've got different percentages for different isotopes. Okay, hydrogen, for example, has 3 isotopes. There's hydrogen 1, called regular hydrogen. There's hydrogen 2, which is called deuterium, and then there's even hydrogen 3, which is radioactive, and it's called tritium. So there's 3 different versions of hydrogen. Hydrogen 1 has 1 proton and no neutrons. Hydrogen 2 has 1 proton and 1 neutron. We're not worried about electrons here. Hydrogen 3 has 1 proton and 2 neutrons. So notice that the number of protons is the same because it is hydrogen, but the number of neutrons is changing, right? So that's an isotope. Iso means same, so same element. It's a version of an element with a different mass. Okay. All right, we did this one. What is an average atomic mass in grams of lithium? If 7.42% is lithium-6 with this mass, and this doesn't matter right here, but we need the percentage. We divide that by 100. And what I do, guys, is I actually just grab that decimal and I slide it 2 places to the left, and that'll change it to a percent. So that's 0.0742, right? Plug this in the calculator. That's 7.42 out of 100, right? If I did 7.42 divided by 100, I get that number. So what you can do when you get your percent is just move the decimal place 2 places. Like this one. This one is 92.58. Just grab that decimal and move it 2 places right there. 0.9258. And that'll be my percent abundance that I put in my equation. All right, let's see how we did this one. We did the percent as a decimal. Notice we got the same exact thing I wrote a second ago, times its mass. And I would keep all the digits here. I wouldn't round much of this. Round at the end, okay? So notice that our answer has 3 significant figures right here. That's because that's the least number of significant figures given in the problem. And try not to worry too much about sig figs. We kind of been spending a lot of time with them. They're important, but not that important. Okay. A mass spectrometer is an instrument that will determine the different isotopes in a sample. So what happens is the isotope is ionized. It is made into a gas, and it's a charged gas. All right, and so now it's a gas, and it's charged, and it's going to go through a magnetic field. And so what happens is it is deflected based on its weight, because now it's a gas. So faster gas particles will move farther, and heavier gas particles will move less so, right? And so then they'll be separated, and you can tell which isotopes are in a sample. So it's based on the magnetic property between the ions that are in a gas state flying through this thing. They're shot through this thing like a particle accelerator, and then they interact with this magnetic field because they're charged particles going through a magnetic field, and so they're deflected. And then the faster ions that are lighter will move faster, and the slower, heavier ions will go down. And so that's how we determine the different weights of those isotopes. So here's what the graphs look like. This is an example of neon 20, and so we can see that this peak ion beam intensity tells us that the main isotope in that sample is neon 20. This one shows us 91, which I'm trying to remember. Oh, 91%, so relative number of ions. So this is also neon because the mass is 20 here, but there's some other neon that's heavier, and then there's some that's lighter, and so the average is going to be a little bit higher than 20, right? I can't remember off the top of my head what the average atomic mass of neon is, but it would be a little bit above 20, just barely, because that 22 is going to bring it up just a little bit. Not much, because there's not much. There's only 9% for that, 91% for this other guy. So it's going to be close to 20, but a little heavier than 20. Okay, this is for natural copper. Most copper is copper 63, and then some copper is this much. And so the average is going to be between these two values, but it is going to be closer to this guy because this is 65%, right? And this is 25%, I think, 35%. So since most copper is 69.09, is that percent? Oh, that's the percentage. Okay, whoops. So since most copper is 63 with 69%, that means that the average is going to be close to 69, or close to 63, but a little bit in between 63 and 65, right? So this 65 is going to bring that average up, but not much. This is cool. I'm doing the notes on the iPad right now. So I finally got my iPad working like I want at home. I got it working at school, but I got it working like I want at home, which is cool. I had to buy the software that I have at school, but totally worth it because I really like this using the iPad. What element results in this? So if we look at this, we've got 202 here. So that is mercury. So we did that one. 1 mole is the number of carbon atoms in 12 grams of pure carbon, which is equal to 6 times 10 to the 23 atoms. Okay, but that's the definition of a mole. It is a counting unit. It is the SI metric unit for counting, or for amount of a substance, like a chemical or a powder or a liquid substance. Here's some mole conversion factors. 1 mole is 6 times 10 to the 23 particles, ions, atoms, or molecules. 1 mole is equal to the molar mass or the atomic mass of a compound or an element. 1 mole is also equal to 22.4 liters of a gas. Okay, and we'll be hitting that again when we hit gases. So here's an example that we did combining some English units with mole conversions. So we started with ounces, we converted to pounds, then we converted to grams. Once we know grams, we can use the molar mass of gold. So we use the molar mass of gold right here from the periodic table, and then we can figure out the moles of gold from ounces. So this was a really cool problem. All right, so we got moles and then we get atoms. Once you know the number of moles, multiply by Avogadro's number, and you get the number of gold atoms. That's a lot of gold atoms. All right, what's this doing? Let's go. Molar mass is the mass in grams of 1 mole of a substance. The mass of 1 mole of an element is equal to its atomic mass. All right, we did this one. We've calculated the molar mass, molecular mass. Now keep in mind, let's watch here. This is the most important part of this example is our inventory. If you look at that, that's 1 platinum. So we're going to do 1 times the weight of platinum, okay, whatever that is. And then we're going to do, look at this. This is 2 nitrogens. There's 2 NH3s. So that's 2 nitrogen. So it's 2 times 14.01, the mass of nitrogen. All right, then we got 6 hydrogens. There's 3 in each of them, and there's 2 groups. So that's 6 hydrogens. So that's 6 times 1.008. I think that's the mass of hydrogens. If not, that's pretty close. And then we got 2 chlorines, right? So 2 chlorines, which is 2 times 35 or so. And so we multiply these out, we add them up, we get our total molar mass. You got to make sure that you distribute correctly in these and count your atoms appropriately and correctly. All right. And so we did that, and this is what we get. We get 300.06 grams. If you're counting and adding up molar masses from the periodic table, you usually want to keep 4 or 5 significant figures. About as many that you get off the periodic table, like these numbers right here from the periodic table, you want to try to keep usually at least 4 sig figs for those kind of numbers from the periodic table. That would be a good recommendation. All right, how many grams are 3.25 moles of cisplatin? So we got 3.25 moles. We multiply that by the molar mass. Moles cancels, and we get the mass of cisplatin, which again is a cancer-treating agent. Percent composition is the mass percent or percent by mass. We take the total mass of each element and divide by the total mass of the compound. Then we multiply by 100. Okay, and that'll give us percent. You have to multiply by 100 at the end. All right, so find the percent composition of all elements in cisplatin. So we take the mass of platinum from our inventory, divided by the total molar mass times 100, and we get 65%. We take the mass of nitrogen. Now let me circle this. This is not the atomic mass of nitrogen. This is the total mass from nitrogen. Remember that we have 2 nitrogens here. See this right here? 2 nitrogens. So that's 2 times 14, which is at 28. Remember, it's the total. So that's one very common mistake is students will put the atomic mass right there. Put the total mass from that element. All right. Hydrogen, 6 over 300. Remember, we have 6 hydrogens. Each is about 1. So we get 6 over that times 100, and we get our percents. Now, you can check your answer. How can you check your answer? Add these guys all up and see if they add up to 100. Those suckers better add up to 100, because that's all the elements in the compound. If they don't, check your work. Awesome. Determining the empirical formula of a compound. There's 2 things here. So there's the empirical formula, which is the simplest whole number ratio of the various types of atoms in a compound. Okay, so it is the simplest possible ratio between elements in a compound. Okay, so the example that I gave before is sugar. Oh, I didn't do sugar. I did methane, but let's do sugar this time, because maybe a different example might make sense. So the glucose is a type of sugar, and it is C6H12O6. Okay, so that is a molecular formula for glucose. That's the molecular formula, or the formula for that molecular compound. But it's not the simplest formula, right? If I divide each of these guys by 6, what's the simplest possible ratio if I simplify it, right? I got 6 out of a 6, that's 1. I got 12 out of 6, that's 2. 6 out of 6, that's 1. Look at that. That's my empirical formula. So that's the difference between them. I know you guys were wondering. So I hope that this is exciting to get that. So that's the empirical formula. Okay, so you can take the molecular formula and divide it into its smallest whole number ratio between those atoms. You can't have smaller than the whole numbers. only whole numbers. Now, how do you get from that empirical formula to that molecular formula to get glucose? Well, you multiply everything by 6, right? And you distribute in, right? 6 times CH2O. And what do you get? C6H12O6. And so you can get that molecular formula back. How do you know if it's a molecular formula? You need the molecular weight or the molar mass of that compound. Okay? So if I told you that the molecular weight of sugar is 180 grams per mole, which is about what it is, how can you determine if C6H12O6 right here is the molecular formula? Well, find the mass of that and compare it to 180. If they are the same, then that is the molecular formula. If they're not, then it's not. Okay, let me show you another way. The formula is CH2O, right? Let's find the molar mass of that. That's carbon, which is 12. Hydrogen is 2. Oxygen is 16. That's 30. That's 30 grams per mole, right? Let's multiply that by 6. 30 times 6, we get 180, right? Yeah, 3 times 6 is 18. So we get 180 grams per mole. So that's how we know the difference between these two, because this is C6H12O6, and this is CH2O. So this is the simplest ratio. This is the actual formula, which is some multiple of the empirical formula. If you multiply every atom and distribute the 6 into there, 6 times the C, C6, 6 times the H, H12, 6 times the O, O6, then you get the molecular formula. So I hope this is clicking. If not, we'll be working with it a little bit more. All right, a sample compound contains 11.66 grams of iron and 5.01 grams of oxygen. What is the empirical formula of the compound? So let's go ahead and write our steps before we solve this one. We have the mass of iron and the mass of oxygen. Let's take the mass of those two elements and go to moles. Okay, so we're going to be dividing by the molar mass. Okay, once we have the moles of iron and oxygen, let's figure out which number of moles is the smallest. Number of moles is the smallest. And then we will divide them into each other, right? Once we know the moles, we divide all mole amounts for every element. In this case, iron and oxygen. We divide those 2 mole amounts, whatever they might be, and we divide them into each other by the smallest number. So divide all by the smallest number. Okay, and then that should be a whole number. Now, if you don't get a whole number, there sometimes is one last step, and you have to make it a whole number. So let's say that we divided them into each other, and we got 1 and 2 for iron and oxygen. Then what's our formula? FeO2. Boom. Okay, so if you ended up dividing this last step, where you divide all of them by the smallest number of moles, when you divide that, you get, let's say we got 1 and 2. Well, then there's 1 iron and 2 oxygen. That's our ratio between our elements, and so that's our formula. Now, let's say that we got 1.5. We might run into an example like this. We might not. So let's say that we did mass of iron divided by mass of oxygen, and let's say we get 1.5. Okay, we can still figure out what the whole number is. We got to just make it a whole number. So let's multiply this by 2. Then what do we get? 3. So if you don't get a whole number, multiply it by something to get a whole number. If you got, you get 1.25, you can even multiply that by 4, and you get a whole number, right? What is that? 1, 2, 3, 4, 5. That'll be 5. So you can make it a whole number. Okay. We might see an example like that. We might not. If not, then maybe I'll find one where we see that. All right. So let's do this one. What A sample of a compound contains 11.66 grams of iron and 5.01 grams of oxygen. So first thing we're going to do is convert the grams of oxygen to moles. So we got that many moles of iron. And then let's do the same thing with oxygen. Convert to moles. So that's our first step. Okay, so we did that here. Go to moles. All right. And then we're going to divide the moles into each other. So here we got 0.2 moles of iron and 0.3 moles of oxygen. This one is less, right? 0.2 is smaller than 0.3. So we're going to divide both of them by that 0.2. So I did 0.2 divided by 0.2, and then I did the 0.3 divided by 0.2. When I divide this, I get 1. When I divide this, I get 1.5. And so I've got 1 to 1.5 as my ratio. Now, if I multiply them both by 2, then that becomes 1 times 2, which is 2. And then 1.5 times 2 is 3. So I know that my ratio between my iron to oxygen is 2 to 3. And so my formula is Fe2O3. That's the simplest ratio. And you guys should be able to tell me what kind of iron that is. In this case, remember oxygen's always a -2. So there's 3 of them. So that's a total -6 charge. So there needs to be a +6 charge to balance. So what is a +6 charge divided by 2 plus 3? So this is iron 3 oxide. And you guys should be able to do that. If not, we'll get there. Okay. What is the empirical formula of a hydrazine, which has 87.5% sodium, nitrogen and 12.5% hydrogen? So this one we're given percents. And the way that you do this one is you can convert percent to grams. And the way that we do that is we assume 100 grams. So let's assume that we have a 100-gram sample. Okay, if I have a 100-gram sample in this example, you can do that. You could assume you have 100 grams. If so, 87.5 grams are nitrogen and 12.5 grams are hydrogen. Okay, so we're going to assume that. We're going to go from grams to moles. And then we're going to take the moles and divide by the moles, just making sure that the one on bottom is the smallest, and we'll get our mole ratios, and that's our formula. Empirical formula, that is, not molecular. All right, so we got mass of nitrogen divided by its atomic mass. We get 6 moles of nitrogen. We take the mass of hydrogen divided by its atomic mass. We get moles of hydrogen. Notice that this one is smaller. Okay, so we're going to divide, I'm going to do it up here, okay, 6.246 divided by 6.246. And then we're going to do 12.38 divided by 6.246. Sorry, my decimals don't come out. There we go. So when I do that over that, I get 1. So we can just write 1 nitrogen in the formula. And over here, we get 2. So that's 2 hydrogens. So 1 nitrogen to 2 hydrogens. Write that formula, NH2. Okay, so this is the empirical formula for a hydrazine, which is nitrogen and hydrogen. Is this an actual molecule that you can look at with a microscope or something? Or if you could get to that, if you could see on that scale and see molecules, is there an actual molecule with this formula? Probably not. But this is the empirical formula, which empirical, if you didn't know, empirical means theoretical. So it's the lowest possible ratio between elements. It may not actually represent a real compound, but it's the lowest possible ratio between elements in a compound. So there may be N2H4, which is, I think this is hydrazine. This is rocket fuel. So we burn this and takes us places. Cool. Okay. Chemical equations. So remember that we have reactants on the left, products on the right, and we have that yield sign, which means that put these things together to make this thing. And so we can write chemical equations as like a sandwich. I usually do this with my regular kids, my on-level kids. I tell them, write me an equation for building a bicycle. You're going to need a seat. You're going to need a frame. You're going to need wheels. You're going to need a handlebar. And so you draw those things separately. And then on the product side, you show a bike assembled, right? Or draw me a chemical equation for making a peanut butter sandwich. You need bread, you need peanut butter, you need some jelly, and then you put it together and you make a sandwich. But you have the same amount of things on both sides, right? You start with 2 pieces of bread by itself, you put it together in a sandwich, and you've got a sandwich with 2 pieces of bread. So you can't create or destroy anything, right? A balanced equation must have the same number of atoms on each side. And then we have symbols to represent physical states. This is a solid, little lowercase l for liquid, G for gas, and then AQ is aqueous, which I think I can spell that, and that means that it's mixed with water. Aqua for water. Mixed. I actually learned a lot of Spanish this summer. Spanish and German. So agua. Okay. Balancing chemical equations. We add coefficients, never by changing the formulas. So if you have water in a chemical formula, if my chemical formula is this, H2 plus O2 makes H2O, right? If I'm going to balance that, there's a certain way that I do that. Y'all should know how to do that. What I cannot do, and I'm going to do this in a different color, what I cannot do is add a 2 there. So, oh, I got 2 hydrogens over here. I got 2 oxygens. Let's just add that 2 right there. If you do that, you change it. This H2O2 is hydrogen peroxide. That's poisonous. You can't drink that. So you had water in your equation. Now you got something else that would kill you if you drink it. So you can't change the equation, right? Let's back up and see how we would solve this. You would obviously need to put a 2 right there. You would need 2 hydrogens and a 2 there. So now you got 4 hydrogens on this side. And I usually make a table. Hydrogen, oxygen, and I do a before and after. So I make a little chart. Okay, so this is reactants. This is my yield. That's my arrow there. It's hard to draw. And then that's my products. So over here, I got 4 hydrogens. Over here, I got 4 hydrogens. Over here, I got 2 oxygens. That's a 1 in front. We can make that a big 1. Over here, I got 2 oxygens. 1 for each molecule, and there's 2 water molecules. So as long as this is the same on both sides, we're good. It's balanced. Okay. Now, there are redox reactions that we will do when we hit that chapter, and there's another way to balance them. You cannot balance them by this method, and it's pretty tricky, but we'll do it then. It's kind of fun, but it's a lot. But we'll get to that when we get to that. Discard. Okay. So let's balance these equations. Over here, I got 2 aluminums. Over here, I got 1 aluminum, 2 chlorines. So if we make a chart, which you guys, some of these you shouldn't need a chart, but let's go ahead and do it. Let's say we got 1, 1, 2, 3. So this is what I call the 2-3 trick. I got 2 on one side, 3 on the other side. I need to multiply them to get the least common multiple between them. And so I need to put a 2 in front. And that'll give me 6 chlorines, right? And then I need to put a 3 in front, and that'll give me 6 chlorines. So if I balance out those chlorines, and then I need 2 aluminums. So then let's redraw our table and see what we got. Let's double check if it's balanced. 2 aluminums on the left, 6 chlorines on the left, 2 aluminums on the right, 6 chlorines on the left. Make sure that you're multiplying the coefficient by that subscript. Okay, so I just wanted to go through one. Let's see what else we got. This one, just the same example, yeah. There we go. So 2, 3, 2, 1, 1, 2, and then this one is, is 1, 2. 1, 2, 1, 2. This is all one equation. So lead nitrate right here. Remember, NO3 is nitrate, so that's lead nitrate. It's lead 2 nitrate plus sodium chloride will yield lead 2 chloride plus sodium nitrate. Okay, the AQ means it's aqueous, means it's mixed in water. Solid means it actually precipitates. Do y'all remember that precipitation reaction that we saw where you take two colorless liquids and mix them together and you see a solid? This is what's happening here. We take lead nitrate, which is soluble. All nitrates are soluble, so it's soluble. Sodium chloride is soluble because of the sodium. When you mix those together, they flip-flop. The lead goes with the chlorine to make lead chloride. Now the numbers change because it needs to be charge balanced. So that's why it's lead with 2 chlorines. It's because it's a +2 lead. So you need 2 chlorines to balance that charge. And then you've got the sodium with the nitrate. And again, it's going to make this formula based on charge balance. Sodium is a +1, nitrate is a -1, so you need one of each in that. So now if there's only one nitrate here, NO3, y'all see that? There's only one nitrate here. It just means NO3. If I meant more than one, I would put a parentheses around it, and I would put 2 or 3 or whatever. So if I wanted to indicate more nitrates, that's how I would do it. I would put a parentheses around it and show 2, kind of like I did right here. Y'all see that? NO3 with the 2 on the outside, that means 2 nitrates. Okay. Combustion analysis. We can burn a sample and see the products of combustion, which is burning, adding oxygen to something. So if you take a compound, so it's usually with carbon, like CH4, add oxygen, you'll get CO2 and water. Okay, and so what we can do is burn it, and then we can look at these compounds and figure out what the sample was. We can figure out what the percentage hydrogen is, what the percentage carbon is, and then the rest is oxygen. So all of the carbon that is burned from this sample, CH4, goes into CO2 because the other product is water. There's no carbon in water. So all of the carbon is in CO2, and then all of the hydrogen is in the water. And so if you do this reaction, record the amount of CO2 you make, record the amount of water you make, then you can determine what percentage of the sample is carbon, what the percentage is oxygen, and then you take 100%, subtract the carbon, and then subtract the hydrogen, and what do you get? You get the only remaining element, which is oxygen. So this is the deal here. This is what we're doing with combustion analysis. Additional O2 is added to burn the sample. So there's excess O2. We've got a limited supply of hydrogen. So once we went out of hydrogen, or once we went out of the fuel, whatever the source is that we're burning, whatever the fuel is, when we burn that, when it runs out, then the reaction stops. But we're going to have excess O2. All of the H2 is absorbed in the first chamber, and all of the CO2 produced is absorbed in the second chamber. Increases in the masses of the 2 chambers are used to determine the mass of CO2 and H2O produced. And then from that, we can determine what the sample was. All right, suppose you isolate an acid from a clover leaf, and you know that it contains only the elements carbon, hydrogen, and oxygen. We heat this much of the acid and oxygen, and it produces this much CO2, this much water. What is the empirical formula for the acid? So if you take a compound and burn it, measure the amount of CO2 and water produced, you can determine the formula for that compound. It's really cool. Okay? So we're just going to look at this question now. What is the empirical formula for the compound? Okay? There's another question here, but we'll look at it in a minute. So here are our 2 reactions. Carbon plus O2 makes CO2. So we're taking the 0.501 grams of CO2. Let's convert it to moles of CO2. And what we're trying to do is determine how much actual carbon, what is the mass of carbon from the original sample? All of the carbon from the original sample was converted into CO2. We have the mass of CO2 here, 0.501. And so we're going to convert it to moles in this step. And then we have to do mole to mole from the compound to the element. This is a very important step that students get lost on sometimes, but you have to go from moles of CO2, which is what you got right here. You have to go from moles of CO2 to moles of carbon before you can go to grams of carbon. I know it's a 1-to-1 ratio, but you have to do it, because if you don't do it, you're going to wish you had, because you're going to miss the problem, because like in water. If you go from moles of water to moles of hydrogen, well, there's 2 moles of hydrogen in every mole of water. So you would be half of what you need. All right, so make sure that you're going from moles of CO2 to moles of carbon. And then you can go to grams using the atomic mass. All right, so let's see what we get. 0.136 grams of carbon in the compound. All right, and this is a really good free response question that's usually on the test. Okay. So that's our amount of carbon. So we're just going to save that for later. We're going to use that later and do what we did with the empirical formulas. We're going to find the empirical formula the way we did before with mass. All right, let's do the water. 2H2 plus O2 makes 2H2O. So there's the grams of water. Let's see what we're doing. We're going from grams of water to moles of water. And then, like I said, 2 moles of water to 1 mole of 2 moles of hydrogen for every 1 mole of water. So now you have moles of hydrogen. Moles of water cancels. This is canceled. And so now you got mass of water. I'm sorry, mass of hydrogen. All right, let's see what else we got. Now that's our mass of hydrogen. So now we can figure out our oxygen. We know that there's 0.513 grams of the compound. We can subtract out the 0.137 grams of carbon. That was carbon, and then this is hydrogen. So we add those 2 up and take the original amount that we had, subtract the sum of those 2, and we get what's left. We get the oxygen because there's only 3 elements. All right, so we got 0.364 grams of oxygen. So now we're going to take the grams of carbon, grams of hydrogen, grams of oxygen, go to moles. I love this stuff. This is fun. I hope you guys love stoichiometry as much as I do because I love it. We got moles of carbon, moles of hydrogen, moles of oxygen. We're going to divide them all by the smallest number of moles and then get our whole number ratios, and that's our formula. Wonderful. Let's do it. So we got 0.364 grams of oxygen divided by its atomic mass. We get that many moles of oxygen. We can take the carbon, we get moles of carbon. We take the hydrogen, get moles of hydrogen. Now I'm going to do this on here. The lowest number is the 0.01144. Divide them all by that lowest number because you want the lowest whole number ratio. So that's how you do it. Okay. I think that's a 2. That's a 1. And that's a 1. So C H2O is probably our empirical formula. 1 carbon, right? Because this is carbon. 1 carbon, 1 hydrogen, 2 oxygens. Let's see what we get. Let's see if I did that right. Beautiful. Now, just as a note here, when you actually divide this out right here, you may not get exactly 2. Okay, but you should be very close. 1.98 is very, very close to 2, so we can round that to 2 because remember, it is a whole number. So just keep in mind that when you divide these mole ratios out, they should work out so that they are very close to a whole number. And like I said, sometimes you might get something like a 1.5 or a 2.5 or a 1.25 or maybe even a 1.33, and you may need to multiply by something to get a whole number. So this one you would multiply by 2. This one you multiply by 2. This one you multiply by 4. This one you multiply by, I think, 3. You can get a whole number because if it's a 0.33, then you can make it a whole number. Now you can't take 1.98 and multiply by something to get a whole number. Right? You can't do that. What you do instead is you round it. So if you're very close to a whole number, you can round. But when I say very close, I mean very close, not 1.5. Yes, technically, you know, we're all taught that 5s round up, but you cannot round a 1.5 up when you're doing empirical formulas. You have to multiply it by 2 to get the simplest ratio. You cannot round that 1.5 up. Okay. What else we got? I could do this all day. So that's our empirical formula. What are we doing here? I'm not sure what we're doing here. Oh, we're getting the molecular formula. Let's go back. Let's go see what our question is. We got our empirical formula. Let's go back. I got to click back a million times. Let's go back to our question. All right, we found the empirical formula of the acid. Given that another experiment has shown that the molecular mass of the acid is 90.04 grams per mole, what is the molecular formula? So let's do that. So 90.04. So that's the molecular weight. Okay. Our formula was CHO2. Okay. So to determine the molecular formula, we need to find the empirical mass. Okay, so step one is to find the empirical mass and then compare that empirical mass to the molecular weight. All right, so this is 1 carbon, 1 hydrogen, and 2 oxygen. So that's 12 plus 1 plus 32. That's 4, 5, 3, 4. So that's 45 grams per mole. All right, and the way that we're going to compare it is we're going to divide it. We're going to do what is the molecular weight or molecular mass divided by empirical mass. So what is 90 divided by 45? Well, that's just 2. So I know that the molecular formula is twice this empirical formula. So we're going to multiply that. So we're going to do 2 times CHO2 and distribute like that. So we're going to get C2H2O4. I think this is oxalate or oxalic acid. I think that's what this is, oxalic acid. Could be wrong, but I think that's what it is. All right, so let's look. We did all this. We did all this. Here we are. So we got that one. So our total empirical formula mass, the mass of that empirical formula is 45. We divide the molecular mass by the empirical mass. We get 2. We multiply it by 2. So C2H2O4 is our formula for this compound. All we did was burn it and weigh the products, and we figured out what it was. So this has applications in forensics, right? You can burn stuff in the lab and record the results and determine what the compound was. That's pretty miraculous, right? That's pretty cool. All right, writing chemical equations from a description. So here, phosgene is combusted in air to form gaseous water and solid diphosphorus pentoxide. So let's write some of that stuff. So we already know the formula for this. It's combusted in air, which is O2. It's going to form gaseous water, which is H2O, and solid diphosphorus pentoxide, P2O5. So pH3 plus O2. This is a nasty reaction, by the way. We're going to form water and P2O5. And then we balance. I think I need to put it. So just a couple tricks when balancing is do your metals first. So first metals, and then do your polyatomics next, which we don't have any in this case, like nitrate. Since it's a group, you can sometimes you can balance it as a group, right? If you have NO3 in a compound on both sides, you can balance that NO3 all as one group, and it'll make it easier. And then you want to do your nonmetals, not including hydrogen and oxygen, and then do your oxygen and hydrogen last, because they're going to be in many compounds. So with that said, we're going to balance that phosphorus first. Over here I got 2, so we're going to go ahead and make it 2 here. Then I'm going to balance the hydrogen. Here I got 2. Here I got 6. I'm going to go ahead and put a 3 there. That'll give me 6. 3 times 2 is 6. Then let's look at the oxygen. I got 5 here. Oh, I got 2s here. I got odd on this side. I got even over here, and they got to match. So I'm going to have to double this. And then this is going to be, so that's 2 times 5, which is going to be 10. And then I can put a 5 there. So that'll give me 10 oxygens on both sides, right? 2 times 5, and then 5 times 2 is 10. And then we can redo the rest. So now I need 2 phosphoruses, And then I need 6 hydrogens. So I think that's balanced. 2, 5, 3, 2. 2 phosphorus. Oh, no, that's not right. We need 4 phosphorus. 4 phosphoruses. And that'll give me 12 hydrogen. So then I'm going to need, what, a 6 there? All right, and then I got 502. I'm struggling on this one. The problem is the oxygen's together. So let's restart. Maybe I'm not writing the products properly. I hope I'm writing this equation right. So I forgot to count up the, so let's do the phosphorus again. That's going to be a 2. That's going to make it 6. So that's going to make this a 3. So that's 3 plus 5, that's 8. So maybe I can put a 4 right there. And I think that's balanced. 2 phosphoruses, 2 phosphoruses, 6 hydrogens, 6 hydrogens. All right, that's 6 right there, 6 right there. And then I got 8 oxygens. I got 5 there plus the 3 there, which is 8. So that's our balanced equation. I messed that up. Apologize. Let's try this next one. When ammonium gas is passed over hot liquid sodium metal, so ammonia gas is NH3, and that is one that you guys need to memorize, is passed over hot liquid sodium metal, which is sodium. Hydrogen is released, and sodium amide is produced as a solid. So let's balance this. 1 sodium, 1 sodium. So I'm going to do the metals first. Then I'm going to do that nitrogen, that's 1. Then let's look at hydrogen. So here I got 4 hydrogens. Here I got 3. Tricky. 1 sodium. Am I doing this right? 1. When ammonia gas is passed over hot liquid sodium metal, hydrogen is released, and sodium amide. NaNH2. Let me rewrite this because I can barely read it. NH2. All right, so 1 nitrogen, 1 nitrogen. I think we're going to try the 2-3 trick here. So that's going to be 6 hydrogens. And now I need 2 of these. So then I need 2 of those. So now let's look at this. 2 nitrogens. I got, this is a 2, sorry. That's 2 times 2, that's 4 hydrogens. Over here I got 6 hydrogens. So if I got 4 hydrogens there, I just need 2 more. And so I could probably put a 1 right there. Let's try that. So 2 nitrogens, 2 nitrogens, 2 sodiums, 2 sodiums, 2 nitrogens, 2 nitrogens, 2 sodiums, 2 sodiums, 6 hydrogen, 1, 2, 3, 4, 5, 6 hydrogen. Yeah, so this is good. So 2, 2, 1, 2. All right, those are fun. Is that what I had? I'm not sure. I'll have to go back and look at my video and see if that's what I had. This one's the same. This one might have been different. But maybe that might have been what I have. I'll have to look. Okay. So we do have some assignments. Chapter 2 problem set number 1 is due today. So if you can get that turned in by the end of the day. NIMSY notes number 3 is due Sunday. And I try to give you guys plenty of time, but please do these as soon as possible because as soon as I give them to you, we're going to be starting that chapter. And if you can watch them beforehand, then you will be in really good shape with the content, right? You will have the background knowledge to do some of this AP stuff. So if you watch those videos and then attend class, it'll click and you'll be much better off, okay? Our tests, chapter 1 through 2, will be on Wednesday. So here's what we're going to put on the test, and I'm still working on it. We're going to put all that chapter 1 stuff like the metric system, conversions of any kind, dimensional analysis, sig figs, scientific notation, atomic structure. I know we didn't do much with electronic structure. We'll hit that later. And we probably should have, but I didn't want to drag this chapter out any longer than we needed to. We're not going to have stoichiometry, but we're going to have moles, percent composition, We're going to have empirical formulas. We're going to have combustion analysis. Basically everything we've covered. And I won't start I won't start stoichiometry today. We'll start that after our test. All right, let's see what else we got. Yeah, so this is kind of stoichiometry. So the trick with stoichiometry is that you're given information about one reactant and then asked to find, so we're given mass of lithium nitrate right here, this one, and then we want to know how much of this is produced. Okay, so that's stoichiometry. So let's see how we would do this one. So we would take the mass of this one, convert it from moles to moles, and then once you have moles of that, you can use the coefficients in the balance equation to go from moles of this guy to moles of this guy. Okay, and that's what we did in this step. Then once we have the number of moles of NH3, then we can use the mass to get the molar mass of NH3 to get the mass of NH3. So that's stoichiometry, where you go from one unit to another, one substance to another in a chemical equation. And then the rest of this, we've got a limiting reactant to talk about. How do you determine which is limiting? And then if you have a limiting reactant, you also have an excess reactant. And so sometimes you can figure out how much of that excess reactant is left over after the reaction stops. So that's another problem we could do. We've also got in here, and I'm just kind of showing you this real quick before we're done. We got percent yield, theoretical yield. So we'll do some of this stuff. And I've got a lab that we'll do for this stuff. I'll demonstrate it, and I will, or I'm going to try to. I'll see if I got the stuff for it. I can't use Bunsen burners in my room because the gas leaks. So we can't use Bunsen burners, but I might try to buy something to where we could heat up stuff. Hell, I could use a blowtorch. I've got a blowtorch. That's always fun. So I could just heat it up with that. But it's baking soda, so we could take baking soda and decompose it and measure the products that we get when it decomposes, and then we can use stoichiometry in our calculations of theoretical yield to prove which reaction happens. There's 3 possible reactions that happen, and so what I'll do is I'll do the lab, and then you guys will need to prove which reaction happens. This is one of my favorite kind of early labs that we do, and it's an AP lab, so it'll be good to do. So I'll demonstrate the lab. I'll show you how to do it, or maybe I'll find a video of somebody doing it if I can't do it myself. And if I can't do it myself, I apologize, but it may be possible, it may not be possible, so we'll see. I'll see what I can do. What else? We've got another equation here with theoretical yields and actual yields, and that's it. That's chapter 3. There's a lot more stuff that we're going to do in this chapter, but we'll get to it. After this chapter, we will talk about solutions and solution stoichiometry. Then when we're done with that, we'll get into kinetics, which is purely AP stuff and usually not even covered at all in the first year chemistry. So thank you guys. I hope this was helpful. Meet me back in the Google Meets to discuss things, and I might have an assignment for you guys. I might have you do something additional in class. Make sure you did the warm-up today. Make sure you submitted it. And that's it, guys. Thank you. Have a great day. It's been fun.